If you or a loved one is taking chemistry with Mr. Tagami, please consider studying. Just listen to what one of our satisfied customers has to say.
When I found out that I had chemistry with Mr. Tagami, I started studying right away, and the results were amazing. I got A's all semester.
Side effects of studying can include, but are not limited to, headaches, anxiety, nausea, stress, acne, and depression. If you begin experiencing any of these, please ignore them because that means it's working. Call 1-800-408-2016 and start studying today.
Hey kids! What are you guys doing?
Chemistry?
Sounds boring.
It is.
What kind of chemistry?
Like chemical bonding, naming, reaction, and stoichiometry.
Do you mean stoichiometry?
Yeah.
Instead of having to read about it, why don't I just show you?
Yeah, okay.
Follow me.
Where?
Just exit out of frame. Welcome to the second dimension.
It's so dark.
Yeah, you get used to it. Also, remember how I said you wouldn't have to read? That was a lie. You're still gonna have to read. Not much though, so don't stress. What do you want to learn first?
Let's start with chemical bonding. What is it and how does it work?
Well, to start, a chemical bond is a mutual attraction between the nuclei and valence electrons of different atoms. There are three types of bonds: ionic, covalent, and metallic. An ionic bond forms between anions and cations. Typically, this involves a negatively charged nonmetal atom and a positively charged metal atom. Atoms are transferred in ionic bonds. For example, sodium chloride is made when sodium gives its one valence electron to chlorine. Both ions now have filled outer electron shells and are satisfied. In covalent bonds, electrons are shared, not transferred. These types of bonds are only formed between nonmetals. Bonds between atoms of different elements are almost never purely ionic or covalent. Bonds lie on a spectrum. You can tell what type they are by calculating the differences in electronegativity of the atoms. In covalent bonds with a significantly different electronegativity, the electrons are more strongly attracted to the negatively charged atoms. These are called polar bonds. Because of the electron's attraction, the resulting molecule has an unequal distribution of charges.
So, does that mean it's unbalanced?
No, it's balanced. It's just slightly more negative on one side than the other. But I'm glad you asked because polyatomic ions are groups of covalently bonded atoms with a charge.
How do you tell what number their charges are?
Ooh, I'm sorry, but there's really no way to tell. You just have to memorize them all.
Oh.
Are you ready to move on to the rules of naming?
Wait, you didn't even talk about the metallic bonds.
Oh, you don't need to worry about those. The only thing you should remember is that they only form between metal atoms. Moving on, when you make compounds, you have to remember several rules about naming them. Some of them are easy and some of them aren't. For ionic compounds, it's just the name of the metal, then the name of the nonmetal with IDE attached to the end, like how sodium and chlorine make sodium chloride.
That sounds easy.
Oh, hold on. It gets worse. If the ionic compound you're naming has a transition metal, you have to write its charge in Roman numerals.
Ew. Why?
Transition metals often have multiple oxidation states, giving them varying charges. If I were to write out Cu2S, I would write it as copper 1 sulfide. Because sulfur has a -2 charge and there are two copper atoms, each atom must have a +1 charge.
Ugh, are the rules for covalent bonds like this too?
No, you use the same IDE ending rule, but that's about it. For covalent bonds, you have to pay close attention to the subscripts, because they'll tell you what the prefix should be.
Prefix?
Yeah, covalent bonds have prefixes. Like in CO2, oxygen has a subscript of 2, so I'd write it as carbon dioxide. If there's only one atom, the prefix would be mono, except if the atom is in the beginning, then you wouldn't use the prefix.
What?
Okay, like If I wrote out CO, it would be carbon monoxide, not monocarbon monoxide. You don't use the prefix on the beginning element.
Oh, I get it.
Great! Well, that's it for naming. Moving on. Do you guys like math?
Not really.
Oh, well, too bad. You need it for chemical equations. It's not hard though. All chemical equations have to be balanced, which means that they have to have equal numbers of each type of atom on both sides of the arrow, like this.
Oh, that's not so bad.
Pretty easy, right? A chemical equation represents, with symbols and formulas, the identities and relative molecular and molar amounts of the reactants and products in a chemical reaction. A coefficient is a small whole number that appears in front of a formula in a chemical equation. It represents relative, not absolute, amounts of reactants and products. Formulas can also be represented in words using the names of the elements. For example, carbon and oxygen combine to create carbon dioxide. Chemical reactions can go both ways, whether it's two elements combining to form one compound or one compound breaking into its base elements. These are known as reversible reactions because the product forms into its original reactants.
This isn't as hard as I thought it would be.
Don't speak so soon. We haven't even gotten to stoichiometry yet.
Oh no.
Stoichiometry comes from the Greek words stoichion, meaning element, and metron, meaning measure. There are two different types of stoichiometry. Composition stoichiometry deals with the mass relationships of elements and compounds. Reaction stoichiometry involves the mass relationships between reactants and products in chemical reactions. Luckily, for you non-honors chem students, we'll only be focusing on the latter type.
Thank God.
Reaction stoichiometry is based on chemical equations and the conservation of mass. All of its calculations start with a balanced chemical equation. This will provide us with the relative numbers of moles of reactants and products. There are 4 different types of stoichiometry problems, each classified by the information given and the unknown, aka the part you have to solve for. The given and the unknown can both be reactants, they can both be products, or they can be one and the other. Either way, you won't know until you solve the problem. Doesn't that sound like fun? Yeah, I didn't think so. Mass will generally be expressed in grams, but other units such as kilograms or milligrams can be used as well.
So, how do we actually solve one of these problems?
If you want to solve a reaction stoichiometry problem, you'll need a periodic table so you can determine molar masses. Molar mass is the conversion factor that relates the mass of a substance to the amount in moles of that substance. Next, you can use ratios from the balanced equation to convert the given quantity using specific methods for each type of problem. Problem type 1. If the given and unknown quantities are amounts in moles, use the given to determine the unknown. Problem type 2. If the given is an amount in moles and the unknown is a mass expressed in grams, find the unknown in moles first and then find it in grams. Problem type 3. If the given is a mass in grams and the unknown is an amount in moles, find the given in moles first and then find the unknown in moles. Problem type 4. If the given and unknown quantities are masses in grams, find the given in moles, use that to find the unknown in moles, and then finally convert your answer to grams. When solving stoichiometry problems, you need to use mole ratios to convert from moles or grams of one substance in a reaction to moles or grams of another substance.
What's a mole ratio?
A mole ratio is a conversion factor that relates the amounts, in moles, of any two substances involved in a chemical reaction. Chemical equations are vital to all stoichiometric calculations because you obtain mole ratios from them. If you want to solve any reaction stoichiometry problem, you have to start with a balanced equation. They help us make predictions about chemical reactions without having to actually test them.
What do you mean by that?
Well, in a real lab, reactions are rarely carried out with exactly the required amount of each of the reactants. Once you run out of one reactant, you can't form any more product. The substance that gets entirely used up first is called the limiting reactant. Also known as the limiting reagent, this limits the amount of the other reactant that can combine and the amount of product that can form in a chemical reaction. The substance that doesn't get completely used up is the excess reactant. In an ideal stoichiometry problem, you'll receive a theoretical yield of product.
What's that?
A theoretical yield is the maximum amount of product that can be produced from a given amount of reactant. In most chemical reactions, the amount of product obtained is less than the theoretical yield. This is due to a number of possible problems, such as impurities or incomplete reactions. So along with the theoretical yield, there's also the actual yield, which is the measured amount of a product obtained from a reaction. When the actual yield is divided by the theoretical yield, then multiplied by 100, this creates the percentage yield, which shows how efficient the reaction was. This is the number that most chemists care about. Well, I think that's everything. We covered chemical bonding, naming, reactions, and stoichiometry. I hope that was helpful.
Wait, how do we leave?
Oh, honestly, I don't know. I guess you're stuck here. I can teach you about chemical equilibrium. What are you guys doing?